All right, so take a second, read this question, and see if you can answer it. All right, so a constant net force acts on an object. Describe the motion of that object with a constant net force. Now, the idea is that you have a net force. Net force means that you're going to have an acceleration, right? So it's not going to be a constant speed and not going to be a constant velocity, because a net force produces an acceleration. Now, because it's a constant net force, then you're going to have a constant acceleration, not an increasing or decreasing acceleration. All right, so constant acceleration because you have a constant net force. That's Newton's second law. Net force equals mass times acceleration. All right, so in this question, it says that there's a force being applied, and let's assume that is the only force that's being applied. And you have an object that is starting at 0. It takes 5 seconds to get to some velocity. We don't know what that velocity is. The force acting on it is going to be 20 newtons, and since that's the only force, that's going to be the net force. And then we have a mass of 5 kilograms. All right, so net force equals mass times acceleration. They kind of skipped a step here where they dropped the summation because there's only one force acting, right? Now, that's going to be equal to mass times acceleration. I don't have the acceleration, but what I can do is I can use kinematic equations in order to determine what the acceleration is. Acceleration is going to be change in velocity over time. So we can plug that into our equation here, mass times acceleration. Then we go ahead and put that in. We get mass times change in velocity over time. The change in velocity is final velocity minus the initial velocity divided by time. All right, now we're trying to figure out the final velocity. All right, we want to get to this variable right here. So we need to get everything else on the other side. We divide by mass, multiply by time, and then we're going to add our initial velocity. Now you notice they don't have the initial velocity in here, and that's because our initial velocity was 0, so they basically just dropped it. All right, plug in our numbers, 20 times 5 divided by 5, that gives us 20 meters per second for the final velocity. All right, so average force required to stop a 1,100 kilogram car in 8 seconds if the car is traveling at 95 kilometers per hour. So we got a mass, right? And we got a time, and we got this velocity here. Now it's traveling, and what we need to do is we need to stop, right? So this is an initial velocity, and then our final velocity is the velocity when it stops. All right, so mass, time, final velocity, initial velocity. All right, so final velocity, initial velocity, and time, that can give us acceleration. And to find average net force is going to be equal to net force equals mass times acceleration. That's Newton's second law. All right, so the average force or average net force is the total force acting on it. Because we're moving forward, right, we have this forward velocity, and we're going to have an acceleration backward, which means our net force is going to be backwards. All right, so go ahead and plug this in. We got the final velocity equals initial velocity plus acceleration times time. These are two equations that's going to help us to get to our average net force, okay? Because we need to solve for acceleration here, and then plug that in for our Newton's second law, and we get mass times this value. So we got everything here. Now there's a slight issue here, right? The final velocity is 0, okay? So that goes away. But the initial velocity is in kilometers per hour. Kilometers per hour. We have to convert that. That's got to be in meters per second. Now, when you convert that meters per second, 1 kilometer is 1,000 meters, and then hours is in the denominator here, so hours converted to seconds. All right, so we multiply everything on top, divide by everything in the bottom, and you get that the net force is going to be equal to negative 3,600 newtons. All right, so read this question, see if you can answer it. It says a net force F accelerates a mass m with an acceleration a. If the same net force is applied to a mass of 2m, then the acceleration will be what? Well, first off, if you think about an object's inertia, so you have the same force, but it's applied to more mass. Now, think about your experience. If you have one object that is light and one object that is heavy, which one are you going to be able to accelerate more? Right? The light object, the one with less mass, is easier to accelerate. So the one that has more mass should have a smaller acceleration, which means that A and B are out. All right, so with a smaller acceleration, it's either C or D. Now, if you think about the equation, Newton's second law says net force equals mass times acceleration. So the force is constant. The force is the same on the left side. So if I have twice the mass, then I need to get rid of that 2 in order to give me the same amount of force. So I have to have half the acceleration. All right, so net force equals mass times acceleration. With twice the mass, that would give me half the acceleration. All right, so again, twice the mass. As the mass doubles, the acceleration would be half, and that would give me the same value on this side, the same value for the net force. All right, so this cable supporting a 2,125 kilogram elevator is a maximum strength of 21,750. What's a maximum upward acceleration that can give the elevator without braking? All right, so we're looking at the upward force that is needed, okay, because that upward force has a maximum, and there's the maximum right there. Now that's not the net force, that's just the upward force. So if you just did mass times acceleration to get your net force, that would not give you the answer because you also have the weight of the elevator being applied to it. All right, so let's go through this. Set up the scenario. You're trying to find your acceleration with mass, tension, and gravity. So you've got your object here. All right, so we're going to talk about a little bit about free body diagrams. We actually made a couple before, I just didn't refer to it. So let's talk about it here. A free body diagram is a diagram where you have a mass, an object, where forces are being applied to it. Okay, this is a terrible dot. Let me redraw that. All right, it's kind of hard to, yeah. All right, so if you start with an object represented by a dot, then the forces being applied are going to be applied to this dot. So we got a mass, this object that has the upward force of tension, and we'll call that, I like to use, again, the capital F to designate a force, but I'll put a sub T for tension. That's the cable that's pulling up on it. And don't forget we have gravity pulling down on it. This is the force, kind of ironic really. Everybody remembers gravity when talking about free body diagrams, but they forget to include it in the equation. All right, so this is your force of gravity. So Newton's second law, net force equals mass times acceleration. So you got your tension upward, right? And then you've got your force of gravity downward, which is mass times acceleration. Now we're going to have an acceleration upward. So we go ahead and add our forces together. Now notice again, we put that negative in there for the force of gravity, but the maximum tension, right, is going to be that tension that's given, and we need to figure out our acceleration. All right, so to solve for our acceleration, simply put, we divide by mass. We have the tension is 21,750. We have mass, which is 2,125 times gravity, which is 9.8. And then we divide that by the mass of the object, which is 2,125. We get an acceleration is going to be 0.44 meters per second squared. So with this cable, if we have any acceleration greater than 0.44 meters per second squared, it's going to snap because that requires more upward force than what the cable can supply. All right, so how much tension is in a rope if you stand, let's see, use an acceleration of 1,200 kilogram car vertically upward at 0.8 meters per second squared? All right, so how much tension's in a rope? Accelerate a car vertically upward. All right, I'll give you a second to go ahead and pause the video and see if you can answer this. All right, so let's go through this. We need to find, let's see, how much tension. We're looking for tension, right? So our force of tension, that's what we're looking for. We're given the acceleration. We're given the mass of the car. So when we're talking about forces, that's going to be Newton's second law. Net force equals mass times acceleration. So we've got to find the tension with respect to mass, acceleration, and we're going to have the acceleration due to gravity as well. All right, so the tension of the object, the car, being held upward. I don't know really what scenario this would happen in, but let's say we do. We got something that's lifting a car. Net force equals mass times acceleration. All right, our free body diagram says we have an upward force of tension. We got a downward force of gravity. All right, and the acceleration is upward. And again, the acceleration is given right here, upward of 0.8 meters per second squared. So what's the force of tension? So tension minus the force of gravity, which is mass times 9.8, is going to be equal to mass times acceleration. You go ahead and take that mass times 9.8 to the other side, plug in your numbers, solve for tension, and you get what looks like 13,000 newtons. 13,000 newtons. That's 1.3 times 10 to the 4th newtons.
So next we talk about the gravitational force. The gravitational force is a mutual force of attraction between any two objects in the universe. So basically when we talk about a mutual force, it's effectively just referring to the reiterance of Newton's third law, that for every force is an equal and opposite force. So when you have the two objects here, you got mass large M and mass small m, they apply a force on each other. That force is going to be the force of gravity. So you got force of little m on big M and the force of big M on little m. Now the idea behind this, one of the misconceptions is that with the smaller mass that you're going to have a smaller force. And the fact is not true. That's the amount of force is going to be the same on both objects because of Newton's third law that every force has an equal and opposite force. So this is our equation. The force of gravity is going to be equal to the gravitational constant times the mass, the large mass, times the small mass, divided by the distance between the two squared. Now you may wonder why we use a letter R when talking about distance, especially when it comes to gravitational force. A lot of times we have one huge object that is essentially the center, and then another object that's orbiting around it or rotating around it, making a circular motion. So with that circular motion, then that gives us a radius of R. But that R is really just the distance between the two objects. Whether or not one is revolving around the other really doesn't matter. It's just that the R just refers to the radius of the circle, but it's also just simply a distance. Now that gravitational constant, that capital G, was experimentally found to be 6.67 times 10 to the negative 11th. This was actually a working together between Newton and Kepler, who Kepler basically made a lot of observations and took some data, and then Newton was the one who was able to formulate the equation and therefore come up with a gravitational constant of G based on his data. All right, so take a second and see if you can answer this question. The gravitational force between two objects is proportional to the product of each other's mass. Now you may say the distance between the two objects, it's actually inversely proportional to the square of their distances, so that's not it. The square of the distances, well, it's not just the square, but the inverse of the square, and then the square of the product of each object's mass. So the numerator isn't squared in this example. So the product of each mass that's in the numerator, so it's proportional to both of those. The radius is going to be squared in the denominator. Actually, with distance in the denominator squared, this is usually what's referred to as the inverse square law when it comes to distance. There's a lot of things in the universe that obey what's called the inverse square law. So the amount of force is going to decrease by the square of the distance. Some other things that you may think of that could decrease by the square of the distance is like electrostatic force. The amount of electrical force between two objects decreases as you increase the distance between the two objects. Light intensity, so how bright a light is, when you move away from that object, the further away you move, the brightness, what we call luminosity, is going to decrease by the square of the distance. All right, so that's referred to as inverse square law. So in this one, it says two objects attract each other gravitationally. If the distance between their centers is cut in half, the gravitational force will what? All right, take a second and try to answer that. All right, so with half of the distance, think about the inverse square law. Half of the distance, the inverse, is going to be 2 times, and then squared is going to be 4 times, which is quadrupled. All right, so half the distance, that means a smaller distance. The thing about a gravitational force is the bigger the distance, the smaller the force. The smaller the distance, the bigger the force. So first off, with half the distance, you know you're going to have a larger force. So that basically cuts out A and B. Those are not going to be possible. And then because of the inverse square law, because the radius is in the denominator squared, then that means it's not just going to be doubled, it's going to be quadrupled. Next one, two objects of mass m1, m2, originally with a distance of r apart, magnitude of gravitational force between them is F. The masses are changed to 2m1, 2m2, and then the distance is changed to 4r. What is the magnitude of the new gravitational force? Take a second and try to answer that. So in this example, we have, if you look at the gravitational force equation, mass is in the numerator. The other mass is also in the numerator. So those are going to be, this is going to double the force, and then this is going to double the force again. So it's going to be 4 times the force. The distance is going to be 4 times, and that's in the denominator, and it's squared. So it's actually going to be divided by 4 squared divided by 16. So you got 4 multiplied by 4, you divide by 16, 4 over 16 gives me 1/4. So it's going to be 1/4 of my original force. Again, because of the equation, how mass is affected affects the gravitational force and how the distance affects the gravitational force. All right, so in terms of G, you may have seen this letter before. Hopefully you have. This is what's referred to as the gravitational field strength, or in other words, the acceleration due to gravity. So at the surface of the Earth, we know what the acceleration due to gravity is, but as an object moves away from the surface of the Earth, the gravitational field strength of the acceleration due to gravity is going to decrease. All right, so gravity is a field. If you remember what the difference between the two types of forces, field forces and contact forces. Contact forces are forces like the normal force, where the two surfaces have to be in physical contact with each other in order for the force to be applied. But gravity is a field force, which means you simply have to be around the object. This mass out in space still feels a gravitational force, even though it's not in direct contact with the object. And that's a good thing, because if you're standing on the surface of the Earth and you jump upward and you're not in contact with the gravitation or the Earth anymore, you want gravity to still pull you down. So we call this G the gravitational field strength, also the acceleration due to gravity. So let's look at the equations. All right, we got the gravitational force between these two objects, and we know that the weight of an object, which is simply the gravitational force, is equal to the mass times the acceleration due to gravity. But we also know that gravitational force is equal to this gravitational constant times mass 1 times mass 2 divided by the distance between the two objects squared. So what we're going to do is we're going to set those equal to each other. And you get that the gravitational constant times mass 1, mass 2 divided by the distance squared is going to be equal to mass times gravity. Now, what is this mass on this side? This mass is the object that's at the surface of the Earth. And for this example, it's the one that's out in space. So large M is the mass itself. What you may notice is you have small m over here for the small mass, and then you have small m over here for what it would be for the gravitational force with the big equation. And hopefully you see that those two actually cancel. And because they cancel, that means the gravitational field strength is going to be equal to the gravitational constant times mass divided by the radius squared. All right, so that is going to be a gravitational field strength equation. And you can figure out what the gravitational acceleration is for the moon if you know how far away the moon is from the center of the Earth, and the mass of the moon, the mass of the Earth. And really, actually, you don't even need the mass of the moon, to be honest. All you need is gravitational constant, which is 6.67 times 10 to the negative 11th, the mass of the Earth, and the distance squared that the moon is away from the center of the Earth. All right, so let's look at this equation a little bit more in depth. Let's look at the surface of the Earth. All right, so the mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of Earth is 6.38 times 10 to the 6 meters. So if we plug all those numbers in, the gravitational constant, 6.67 times 10 to the negative 11th, times the mass of the Earth divided by the distance from the center of the Earth to its surface. Now you got to be careful with that. Just because you're standing on the surface doesn't mean your distance is 0. The distance is measured from the center of you to the center of the Earth. And that effectively is the radius. Now, I guess technically it could be the radius plus 3 feet, however far above the surface of the Earth your center is. But in respect to 10 to the, that's millions of meters, 1 or 2 meters is really not going to be that much of a difference. All right, so with that said, you crank all this out, you get 9.799088059. You can actually plug that in your calculator and get that answer. But what you'll notice, hopefully, is that that is approximately equal to 9.8 meters per second squared, which is why we use that for the acceleration due to gravity at the surface of the Earth. Now, if you're talking about the moon, then you would need to figure out the distance that the moon is away. And hopefully you see moon being pretty far away, if that's in the denominator, the acceleration due to gravity is going to be less where the moon is as opposed to where we are. However, that acceleration due to gravity is enough to still keep the moon in orbit around the Earth.